Okay, hello everyone. Good morning, all of you. Okay, today we start with a nice quote. So it says, the happiest people don't have the best of everything. They just make the best of everything. Okay, so we may not have best of everything, but whatever you have, you use it to the best. Okay, so then you will be happy. And today is the birthday of the great actor, Telugu actor actually. He is no more. He is great Akineni Nageshwara. He is an actor and producer. And he established Annapurna Studios in 1975. So in those days, he has built a very great studio in Andhra Pradesh, Hyderabad, to provide infrastructural support to the Telugu film industry in Hyderabad. He later started the Annapurna International School of Film and Media within Annapurna Studios in 2011. And he is a recipient of the Dada Saheb Phalke Award, the highest Indian award in the field of cinema. He was also honored with the Padma Vibhushan, India's second highest civilian award, for his contribution to the film industry. He's a great personality, and in my generation, nobody will be there who doesn't love him, right? He's a great film actor. Okay, in the last class, we have discussed finite difference formulations or discretization of the partial differential equations into algebraic equations. And we have done that using Taylor series expansion. And we have seen how to get the expressions for any order derivative with first order accuracy. So what we have to do is, if you want first order derivative, take one more additional point, neighboring point. If you want second order derivative, take 2 points, 2 additional points. If it is third order, take 3 additional points. And then we have seen forward difference approximation, backward difference approximation, and central difference approximation. So if you want to have the forward difference approximation, we have to take the points I plus 1, I plus 2, I plus 3, etc. Backward difference approximation, I minus 1, I minus 2, etc. If you want central difference, you take the points on either side. Okay, that is the way we have to go about getting the expressions for any order derivative with first order approximation. And if you want to increase the order of accuracy, so what I have to do is, if I want first order derivative with second order accuracy, then second order derivative with first order accuracy is to be substituted there. And if I want first order derivative with third order accuracy, I have to put third order derivative with first order accuracy, second order derivative with second order accuracy. You have to substitute in the expression so that I can get the first order derivative with third order accuracy. So as I told, we will not be interested with very high order accuracies. Okay, so usually second order, at the max, you may go for third order accuracy. And if you want to increase the accuracy, instead of going for higher order accuracies in discretization, we discretize the domain with the finer grid. Okay, so that is the way we can achieve the same thing. And we have seen how to do the finite difference formulation for mixed partial derivatives, like dou square f by dou x dou y. And that also we have seen with central difference, forward difference, and backward difference. We can do, or we can do the dou by dou f by dou x, dou by dou x of dou f by dou y, or dou by dou y of dou f by dou x, like that you can do and get it. And also we have seen finite difference formulations with unequally spaced grid points. But it should not be any order, usually geometric series. So the first one is delta x, then alpha delta x, then alpha square delta x, alpha cube delta x, like that. It should be of that sort. Then only it will be somewhat easier to do it. Okay, if you want to do finite difference formulation with unequally spaced grid points, usually unequally spaced or any haphazard type of grid, we have to go for finite volume method or finite element method. But if I want to confine to finite difference formulation, but if I want to have unequally spaced points so that the computational time or the load on the computer can be reduced, then I have to go for geometric geometrically varying grid. Okay, so these are the things we have discussed. Just we quickly go through the formulations. So this is today we are going to have discretization using polynomials. Okay, last class the things are Taylor series expansion. So fi plus 1, fi minus 1, fi plus 2, like that you can write using the Taylor series expansion. And for forward difference approximation, you will get fi plus 1 minus fi. For backward difference, fi minus 1, or for central difference, fi plus 1 minus fi minus 1 by 2 delta x. And forward difference, backward difference, their order of approximation is first order, and central difference you get second order approximation accuracy. Okay, and for second order derivative, again you can write forward difference, backward difference, and central difference. And if you take forward difference, I have to consider fi plus 2. So fi plus 2 minus 2 fi plus 1 plus fi, like this, or fi minus 2 fi minus 1 plus fi minus 2 for backward difference. For central difference, fi plus 1 minus 2 fi plus fi minus 1. These are the second order derivatives. Again, forward and backward difference are first order accuracy, and central difference is for second order accuracy. And if you want to have these are the things we discussed today, recurrence relations. Okay, we will complete last class things. Okay, first order derivative with second order accuracy if I want. So already I have got the second order derivative with first order accuracy. This is to be substituted in this expression, dou square f by dou x square. I have to substitute there. And then if you simplify, I am going to get first order derivative with second order accuracy, minus fi plus 2 plus 4 fi plus 1 minus 3 fi by 2 delta x plus order of delta accuracy delta x whole square. So again, I told for verification, you can see that the coefficients, sum of the coefficients will be 0 always. So what I want to say is, it is based on the movement of information. If it is going, the information is moving from left to right, then the values at a point depends on the points behind it. Okay, suppose if the flow is coming this way, then the values of this point depends on the values on this side. Okay, fi plus 2, fi plus 3, like that. And if it is a diffusion type, if the information is going in all directions in the same way, then if values at a point depends on all the neighboring points, and then I have to take central difference. Okay, that is the way we have to decide whether I have to take forward difference or backward difference or central difference for a particular derivative. Right? That's why it is important to have the knowledge of the physics of the problem. I have to know how the information is moving. If the flow is taking place just like this, left to right, as usually happen, then we take the backward difference. Okay. That is, if I want to find out the values at a particular time, I have to use the time in the past, not in the future. Okay, because present depends on the past. So I have to take the value of, if it is n is the present time, n minus 1 you have to use. Or if you want to calculate at n plus 1 point time, I have to use the value at n time. Okay, so that is the way. And so first order derivative with different approximations. You can see here, second order accuracy, forward difference, backward difference, like that. And this is 3-point second order derivative approximations. Okay, this already we have done this. And finite difference approximations using more than 3 points, that is third order derivative and fourth order derivative, and second order derivative with second order accuracy, and the third order derivative with second order accuracy. You can see as the order of accuracy increase. Okay, third order derivative with first order accuracy will be simple, and the second order, because it is central difference, okay, it is taking ui plus 2, small numbers will be there, 1 minus 2 plus 2 minus 1. If I go for forward difference approximation with second order accuracy, it will take I plus 4, I plus 3, I plus 2, I plus 1, I, and it will take minus 3, 14, minus 24, 18, minus 5, like that. Large coefficients will take. So it will be bigger calculations will be there.
Sir, One
Yes,
question is there.
yes,
Sir,
yes.
is there any handbooks regarding all these
Yeah, yeah,
formulations?
yeah. They will be available anywhere, right? Many books are there. Handbooks also, mathematics handbooks. You can take. Okay,
Okay,
no.
sir.
Okay, these things I didn't type. You can observe it. I have taken it from some book only, right? Okay, this we have continued. We have done with unequally spaced points with all the geometrically varying grid distance. So delta x, this is alpha delta x we have taken. And same Taylor series expansions we have to do. So for the second point, when I want to do, then that is I plus 2, then the distance is 1 plus alpha into delta x. So that I have to use. And you can do the same method of simplification. Okay, this thing which I have skipped, I will show you. This is recurrence relations. Okay, if you want to have the expressions for very higher order derivatives like sixth order, seventh order, like that, you can see that there is a lot of algebra involved. But is there any shortcut? If I am happy with first order accuracy, there is what is called as recurrence relation. Okay, so
Sir,
yes.
sir, is it possible like this can be showed, sir, with any numericals so that we would understand it better? Like any problem?
No, no, yeah, yeah. Problems we will see. Problems we will do. These are the things only derivations to get the expressions. Here there will not be any numericals. These are derivations. I think you
Okay.
understand the difference, right? If I want to have the Bernoulli's equation derived, there will not be any numericals there. And after that, we apply the Bernoulli's equation and then we use the numericals. Okay?
Okay, sir.
Okay, here there is what is called as forward difference operator. Delta f, delta x, f I is fi plus 1 minus fi. This is forward difference operator. Okay. Similarly, I will have backward difference operator like this, equal to fi minus fi also. Okay. So if I want second order like delta x2 fi, this can be written like this: delta x of delta x f. Okay. So that is delta x of delta x fi is fi plus 1 minus fi. Okay. So means delta x fi plus 1 minus delta x fi. So what will this be? Delta x fi is I plus 1 minus I am getting. So if there is I plus 1 here, it will become I plus 2 minus I plus 1, right? So it will become I plus 2 minus fi plus 1 minus delta x fi as this fi plus 1 minus fi. So if I simplify it, it will become fi plus 2 minus 2 fi plus 1 plus f. You can see that actually this is the numerator of second order derivative for the forward difference approximation. Okay, it will be something like this. If I want dou power n by f dou x power n, I is equal to delta x n fi by, it will be like this. Okay, so if I want to get dou f by dou x, so n is 1, so delta x fi plus 1 minus fi by delta x. And if I want dou square f by dou x square, n equal to 2 in this expression. So delta x2 means fi plus 2 minus 2 fi plus 1 minus plus fi by delta x whole square. If I want third order derivative, so delta x cube I want third order fi is delta x of this delta x2. Okay, so if I expand this, this becomes fi plus 3 minus fi plus 2 minus 2 into fi plus 2 minus fi plus 1 plus 2 into fi plus 1 minus fi. If there is any doubt or difficulty, you ask me. Okay, so delta x of fi plus 2 is fi plus 3 minus fi plus 2. This is 2 times delta x of fi plus 1. This will become like this. And again, plus 2 times, this is plus 2, like this. So if I expand this, I will get fi plus 3. How many fi plus 2s are there? This is minus 1, this is minus 2. So minus 3 fi plus 2. And fi plus 1s, here plus 2 is there, here plus 2,
4,
so plus 4, fi plus 1. And the fi's are
minus 2
fi. Okay, this is this. So if I want dou cube f by dou x cube, third order derivative, with all these are first order accuracy. Okay, recurrence relations are useful only for first order accuracy. So this will be equal to all this expression I have to write by delta x whole cube. In this way, I can go on going for fourth order derivative, fifth order derivative, sixth order derivative. You can see it will be very easy. But if you want to do with Taylor series expansion, right, and you have to take fi plus 1 to fi plus 3, fi plus 4, fi plus 5 like that, and you have to do the manipulations to see that fi is cancelled. Okay, f dash I and f double dash I are cancelled. So you have to do that manipulation. That is, I have to take the expression of fi plus 3, take the expression of fi plus 2 into 3 I have to do, and you have to see what manipulation I have to do to get this dou cube f by dou x cube in the Taylor series expansion. So there is a lot of mathematics you have to do, but here simply just using the recurrence relation, you can get the expression for any order derivative. Is that clear? Okay, sir. Okay. So yes, same thing can be extended for backward difference also, right? Only thing is reverse delta we will write fi is equal to fi minus fi. So you can write delta x2 fi is equal to delta x and delta x. That is delta x of fi minus fi minus. So delta x of fi minus delta x of fi minus 1. So this will be fi minus fi minus 1 minus, for fi minus 1 I will get fi minus 1 minus fi minus 2, like this. So you will get fi and minus fi minus 1 minus fi minus 2 fi minus 1 and 1 plus fi minus 2. Like this I will get that. So if I want delta x cube fi, so one more delta x of this I have to take. So it will become fi minus fi minus 1 minus 2 into fi minus 1 minus fi minus 2 plus fi minus 2 minus fi minus 3. Like this I will get fi minus 2 fi minus 1 minus 2 fi minus 1 minus 4 fi minus 1. Here 2 fi minus 2 plus fi minus 2, 3 fi minus 2 and minus fi minus 3, like this. So if I want again dou cube f by dou x cube if I want, so is equal to del x cube fi by delta x whole cube plus order of delta x. Like this I can do. Okay, that is the way I can do. And similarly, you can have for central difference also, and there are difference operators like this is forward difference operator, this is backward difference operator, and this delta, okay, this small delta, okay, triangle like thing is capital delta, and small delta will be like this. So delta x star fi, this is fi plus 1 minus fi minus 1, which is nothing but forward difference operator plus backward difference operator. If you add these two, that is uh, fi plus is not written here. Okay. Fi plus 1 minus fi minus fi minus fi minus 1. If you fi gets cancelled, you will get fi plus 1 minus fi minus 1. Similarly, this delta x without star, okay, delta x fi is fi plus half minus fi minus half. And delta x2 fi is delta x of delta x fi. So it will be delta x of fi plus half minus fi minus half. And delta x of fi plus half is it is like this, okay, and delta x2 fi is equal to delta. So delta x of this fi plus 5 minus like this. Okay, if I take this, what I have to do? I have to add half and minus, subtract minus half. Okay, so I will get fi plus 1 minus fi minus, for fi minus half, again add plus half minus subtract half. Okay, so I will get fi minus minus. So here fi sorry, here fi plus 1, here minus fi minus 2 fi and plus fi minus 1. Okay, this is a second order derivative thing you will get. Okay, there are different types of things are there. You can write this forward difference operator, backward difference operator of fi is first you operate so delta x fi minus del x. This is, I call it as del, and this is delta. So this is delta x fi minus del x fi, like this. Okay, and the forward difference operator, it will become fi plus 1 minus fi. The backward difference minus of fi minus fi minus 1, you will get like this. It is same as this, you can see. Okay, so in this way, you can go for higher order. Okay, so this is called as recurrence relation. We will see how it can be used in solving the problems later. And then I'll go for the next topic using polynomials. Okay, this is also we have done partial derivatives. If I take this as dou by dou x of dou x by dou y, and you can use it central difference, or this is using central differences, and this is using forward differences, and even backward differences also you can use. And okay, finite difference by polynomials. So what we do is here, this f is a polynomial. I draw a line like that. Okay, again, you want forward difference, backward difference, or central difference. Usually take this as I. Okay, if I want the forward difference, take the points after this. Okay, that is I plus 1, I plus 2, I plus 3, like that. Okay, if I want backward difference, then I minus minus 1, I minus 2. This is f. This is x. So all these are delta x. Again, if you want central difference, you have to take I minus 1 and I plus 1. Both sides I have to take like that. And depending on what order derivative we want, right, we have to take the expression like that. Okay, f is equal to, okay, if I want a second order derivative, ix square plus bx plus. So I have three constants. Three constants means I should have 3 points. 3 points means I plus 1, I plus 2, I take. So I am taking 3 points means I am going to get second order derivative. So if I want second order derivative, I have to take second order polynomial. If I want third order derivative, I have to write ax square plus ax cube plus bx square plus cx plus d. Like that I have to take. I have to take one more point so that one more constant will be added. Higher order accuracy, higher order derivative, I do like that. Okay, so here, what is that I am going to do? And so this f, so fi is equal to axi square plus bxi plus c, or fi plus 1 is equal to a into xi plus 1. So here xi is equal to 0, right? Because I am taking I at this point. So xi plus 1 will be, what is xi plus 1? Delta x. Xi plus 2 is 2 delta x. Xi plus 3 is 3 delta x, like that. So if I want fi plus 1, then x into xi plus 1 square means a delta x whole square plus b delta x plus c. Here xi is 0, right? So this will be c. Fi equal to c. And fi plus 1 is this. And fi plus 2 is a into, what should I write? 2 delta x square plus b into 2 delta x plus c. Like this I have to write. Okay, what is that I have to do? Whenever I want to have a polynomial, I have constants, I have to solve for the constants. What is that I know? I know xi, fi, xi plus 1, fi plus 1, xi plus 2, fi plus 2, I have the table. Okay, those values I know. So using that, I have to solve for ABC. Okay, so these things I have to solve. ABC I have to solve. In the first equation, I got fi equal to c. So from these two equations, I have to solve a and b. Okay, so this c I can write fi. This c also I can write fi. So I can write fi plus 1 minus fi is equal to a into delta x whole square plus b into delta x. In the next equation, fi plus 2 minus fi I am taking to the other side, is equal to 4a delta x whole square plus 2b delta x, like this. Now I have to solve these two to get a and b. How to do that? So if you want to eliminate b or a from these two equations, so first if I want to get a, multiply the first equation by 2 and subtract it from 1. Okay, so fi plus 2 fi plus 2 minus fi, this is second equation, minus 2 into fi plus 1 minus fi is equal to, okay, so this is 4a, so minus 2a it will be, so 2a delta x whole square, and b terms will go off. Okay, this is the way I get. And so A I can find out. A is equal to Fi plus 2 minus 2Fi plus 1. How many Fi's are there? Minus Fi. This is plus 2Fi. So plus Fi by delta x whole square. Like this I will get. And to get B, I have to cancel A. Okay, so for second equation minus 4 into first equation. So Fi plus 2 minus Fi minus 4 times Fi plus 1 minus Fi is equal to A term goes off. And so this will be 2B minus 4B. Okay, so minus 2B delta x. Like this. So what is that B? I will get Fi plus 2 minus Fi, minus 4Fi plus 1 is there. And minus Fi plus 4Fi. Okay, so plus 3Fi by minus 2 delta x will give me B. So I get A, B, C. Okay, what is that I will get with A, B, C? Now I want first order derivative, second order derivative like that. Okay, so what is F dash? Because Ax square plus Bx plus C is F. What is F dash from there?
2ax plus b
2Ax plus B.
plus
And F double dash is
2a.
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 Okay. Now what I want, F double dash I can directly get it. Okay, this into 2, I will get the second order derivative. Am I right? Second order derivative, we know that this is that. And first order derivative, F dash I is equal to 2A xi plus B. Because xi is 0, this will go off. Okay. And this B is nothing but F dash I. Okay. So here, what is that I am going to get is, because already you know, I am going to get second order derivative. I am actually calculating the second order derivative with first order accuracy I will get. And in the process, you will get F dash with the second order accuracy. Okay. So that is F dash with second order accuracy. So that is the way we get. Whenever, if you want to get it using this, I am going to get third order derivative. It is something like F is equal to x squared plus bx squared plus cx plus d, like that if I write. So again, Fi will be, this will be 0, this will be 0, because xi will be there. So Fi will be d. And the Fi plus 1 is equal to A into delta x whole cube plus B into delta x whole square plus C into delta x plus D. Similarly, Fi plus 2 is equal to A into 2 delta x whole cube plus B into 2 delta x whole square plus C into 2 delta x plus D. And Fi plus 3 is equal to A into 3 delta x whole cube plus B into 3 delta x whole square plus C into 3 delta x plus D. And again, you can see that Fi equal to D. So I can eliminate this. I can write here minus Fi plus minus Fi plus minus, like this. So we got three equations to solve for A, B, and C. So same way, we have to do algebraic manipulations to solve for A, B, and C. And once I solve them, I can do F dash. F dash is equal to, find out 3ax square plus 2bx plus c. So F dash I is equal to So xi is 0. So this and this goes off and c only will be there. And f double dash, I'm going to get 6ax plus 2b. Again, f double dash I, xi, this will be gone, and I will have 2b. And the f triple dash, if I take 6a. Okay, so f3 dash I is equal to 6a. Because I am going to solve a, b, and c, I am going to get third order derivative with first order accuracy I will get, and here second order derivative with the second order accuracy I will get, and the first order derivative with third order accuracy I will get. Okay, though I am calculating this, these are like byproducts. You will get second order derivative with second order accuracy and first order derivative with third order accuracy. Is that clear? Only thing is a little bit involved to solve these three equations to get a, b, and c. And the same way you can do for backward difference and central difference also. Okay, this is the way it is done here. This is, you can see, this is second order derivative with first order accuracy and first order derivative with second order accuracy. Then we have taken only quadratic equation. And this can be extended for unequally spaced grid points also. So here fi plus 1 is a delta x whole square plus b delta x plus c, and fi plus 2 is a into 1 plus alpha whole square delta x whole square. Instead of 2 delta x, I have to put like this, and b into 1 plus alpha delta x and c. And again, you solve it for a and b here. So b I am going to get here, a is I am going to get this. And what is dou square f by dou x square? So we have seen that if I so f dash 2ax plus b and f double dash 2a. So f dash I is equal to b, f double dash I equal to 2a. Okay, so that we know. So f dash I, this is the b itself will become this. Okay, and 2 times this a will become the second order derivative. Okay, so this is the way we get. Again, you can check if alpha equal to 1, then it will become for equally spaced grid points. So it should tally with that. Okay, that is the way we can do for unequally spaced grid points also. And these are the tables given at the end of the first, the second chapter. So you can, as somebody is asking whether data books are there like that, you can take this as some data like that. So if you want dou f by dou x, this is minus fi plus 1 by delta x. And the second order derivative, fi minus 2 fi plus 1 plus fi plus 2 by delta x whole square. And similarly, minus fi plus 3 fi plus 1 minus 3 fi plus 2 plus fi plus 3 by delta x whole cube. Like that, I can have different order of derivatives with first order approximation. This is a table for first order approximation. Similarly, you can have backward difference representation with first order accuracy. In the same way, it will become minus fi minus 1 plus fi by delta x. If you take this, fi minus 4 minus 4 fi minus 3 plus 6 fi minus 2 minus 4 fi minus 1 by plus fi by delta x power 4 gives me dou to the power 4f by dou x power 4, fourth order derivative. In that way, you can have central difference approximation also. Central difference, it will be the order of accuracy, second order accuracy. And here, if you take fourth order derivative, it is fi minus 2 minus 4 fi minus 1 plus 6 fi minus 4 fi plus 1 plus fi plus 2. So by delta x power 4, like this. And you have other tables for second order accuracy also. Forward difference representation with second order accuracy. Okay, for first order derivative, second order derivative, third order derivative, fourth order derivative. These are available. Okay, so if you are asked to derive it, you have to derive it. And if you are asked to use these formulas and relations, you can take this formula directly from the textbook. You need not derive it. Okay, this is forward difference with second order accuracy. And Actually, there will be other two more tables like backward difference with second order accuracy and central difference with delta x power 4 will be there. Okay. This we will do later. Okay. Okay, we will see some problems. They are given a lot of worked out examples are there. I have taken from there only. And determine the approximate forward difference representation for third order derivative. For third order derivative, which is of the order delta x, first order the approximation, given evenly spaced grid points as shown in figure 2.7. Okay, that is previously equally spaced grid points by means of you derive it using Taylor series expansion, using forward difference recurrence formula, and using third degree polynomial passing through the 4 points. Okay, so these three methods you can use any method, but if you use all the three methods, you have to get the same expression. Okay, so you are asked to calculate this using all the three methods. So using Taylor series expansion, I have to get fi plus 1, fi plus 2, and fi plus 3. Then I have to do the manipulation. Because I want third order derivative, I have to see that first order and second order derivatives are cancelled. So that I have to do. It is done like this: 3 fi plus 1 minus fi plus 3, fi plus 2 minus 2 fi plus 1, right? So in that way, here first order derivative is cancelled, and here another first order derivative is cancelled. Then using these two, I have to cancel second order derivative to get the expression, and I am going to get third order derivative. This is the way you are going to get. Okay, so this is the way you can use the Taylor series expansion. If I want to use the recurrence formula, as I told, delta x cube I want, so delta x square of delta x fi. So this we have done already. So like this we have to get it. This is using reference formula. And if I want to use polynomial, I have to use third degree polynomial, because I want third order derivative. So ax cube plus bx square plus cx plus d. So we have to put delta x fi plus 3 delta x we have to put, fi plus 2 delta x, fi plus 1 delta x we have to put. And the fi is d, because fi x is axi cube bxi, xi is 0, so fi is d. And this fi is substituted here, and you take it this side, so that I am going to get three equations, a, b, c unknowns, and that we have to solve. Okay, by solving, the expressions are given, a, b, and c expressions, you will get like this. So from this, dou f by dou x is 3ax square plus 2bx plus c, dou square f by dou x square is 6ax plus 2b, and dou cube f by dou x cube is 6a. Actually, here it is asked only to find out third order derivative. So 6 times this particular expression will give you dou cube f by dou x cube. And if you want, I can find out f double dash with second order accuracy by putting xi here. This will go off 2b. Okay, 2 times this will give me second order derivative with second order approximation. And similarly, dou f by dou xi, so these two gets cancelled, only c will be there. Okay, so this c is nothing but first order derivative with third order approximation. Am I clear about what I am saying?
Yes, sir.
Yes, sir.
Yeah. Yeah, this is done here, right? Okay, this is done here. Similarly, you are asked to find out backward difference approximation, dou f by dou x, which is of the order of delta x whole cube, third order approximation, right? Here already previously we got this is third order approximation for first order derivative. And here, first order derivative with third order approximation for backward difference it is asked. Okay, again you can do any of the method. Okay, if I take this Taylor series expansion, what I have to do is I have to substitute third order derivative with first order approximation and second order derivative with second order approximation. I have to substitute here so that I will get first order derivative expression. Okay, this is this. You can see dou cube f by dou x cube with first order approximation. and this is dou square f by dou x square with second order approximation. These two are to be substituted here, so that I am going to get dou f by dou x with third order approximation. Okay, this is the way we have to go about. And the numericals. Okay, somebody is asking me, there are numericals. And okay, mainly what I want to say is, now this week you will not have minor test, but you will have assignment. Okay, Hoffman book. First volume and first chapter, exercise, problems 5 to 15, and second chapter, exercise, problems 1 to 10. Okay. Maybe I can take it as 6 to 15. Okay, so 10 problems, here 10 problems, 20 problems. So this you have to take it as assignment 1. As I told, these problems are important because similar problems you are going to get in your mid-exam and also final exam. So you have to submit this assignment. You submit this assignment, you take 1 week. Okay, today is Monday. So next Monday, you have to submit. Okay, next Monday by 12 o'clock. So I will create either Google Classroom where you can submit, or you can submit in LMS. So I will tell you, but meanwhile you solve the problem. If I create a Google Classroom, you will get the invitation to join in the classroom. You join it, and you are going to get the assignment. And
Sir, will you
yes.
Will you solve and like scan and make it a PDF?
Yeah, that's right. You have to write it, scan them, and make it PDF. I think you are used to this already. You might have done online classes and submitted assignments, and that. Even children are doing that. So you do it on A4 sheets, and you scan them and make it like a PDF, a single file. Is it okay?
So can we write in digital format?
No digital format. You have to write it. Because, okay, just one thing I am telling, digital format, if all people submit the same thing, right, you need not work at all. You need not work at all, isn't it? Digital format.
No, sir, like you are writing in that pen tablet that way, so that
it should be your handwriting.
Sir, I'm trying to say, like you are writing on this Wacom tablet, like digital tablet.
Yeah,
like
you
that.
write it, but you have to submit it to me in a PDF form with your writing. It will be writing only. It's my writing, isn't it? I am
Yes,
sending you PDF with my writing only.
So that's what I'm saying. Like
Yeah, you can do it. You can do it. No problem. What I am telling is, I have to see your handwriting. Okay. Sometimes you discuss, you can copy others' things, and you can do the same thing, because with discussion only, if you have doubt, anyhow you have to discuss, and sometimes you may share your answers also. I don't mind. You only have to get the confidence in the subject, and I want at least, even if you copy, some people copy, if they write by their own hands, at least they will know what they are doing, and it will be useful. Okay. You can do like that, like Wacom, you can write it, you can take the PDF and submit it. Okay?
Yes.
Thanks. Yeah. Similar problems are there in the exercise. That's why we are going, and similar problems you will get also. And given the function f of x is equal to sine 2 pi x, determine dou f by dou x at x equal to 0.375 using central difference representation of order delta x whole square and order delta x whole power 4. Okay, so you have to have the expressions for dou f by dou x with central difference representation of order delta x whole square and delta x whole power 4. As I told, the tables are available. You can take that expression. You need not derive it. Okay, but actually, if it is offline, you have to derive it. But because it is online, you can have those expressions from there. Okay, and use step sizes 0.01, that is delta x if it is 0.01 or 0.1 or 0.25. As you already know that this is like refinement of the grid. So 0.01 is the step size, means fine grid. 0.1 and 0.25 is the coarse grid. And you can see, compare and discuss the results. We have to do this. Okay, so like this. Now dou f by dou x, this is second order approximation, fi plus 1 minus fi minus 1. This already we know, we have done it. Second order approach, that is higher order, fourth order accuracy, I will get this expression. Okay, so this expression is used. And dou f by dou x, so fi plus 1 means I have to, this xi is 0, and xi plus 1 is xi plus delta x, means 0.01, if this is the spacing, and xi plus 2 is 0.02, and xi plus 3 is 0.03. That you have to substitute here, so that you will get fi plus 1, fi plus 2, like that. If any doubt, you ask me, right? So you calculate using calculator, and these are radians. That is very, very important. Okay, if you put pi in radians, then you have to take this in the calculator, in radians you have to calculate. Okay, so it is left to you whether you want to substitute pi in degrees or radians. Okay, so better use in radians, and 2 into 3.14 into x is 0.01, then 0.02, 0.03, 0.04, like that. So you will get fi plus 1, fi plus 2, like that. And what I have to do is, I have to get at 0.375. Okay, so dou f by dou x, this is like this, and just to substitute the values, you are going to get dou f by dou x this, and dou f by dou x is this. Okay, here, sorry, just at x equal to 0.375. So xi is 0.375. Xi plus 1 is 0.375 plus 0.01. And xi plus 2 is 0.375 plus 0.02. Like that, you have to get it. So that I will get dou f by dou x at this particular point. Am I clear?
Yes, sir.
Yeah. Like that, you have to calculate at this. So dou f by dou x is this. And for the step size 0.1, we got some value. And for the step size 0.25, we got another value. You can then actually which value is good. So I am telling finer grid you will get a better value, and rough coarse grid you will not get a better value, or something like that. So I should have the actual value. True value I can always find out, isn't it, using calculator? Because x equal to 0.375, if you substitute here, directly I can get what is fx at that point. And dou f by dou x, so this is okay. So dou f by dou x for cos sin 2 pi x is 2 pi into cos 2 pi x. So this is analytical derivative. So this here I can substitute here. X is equal to 0.375. If you substitute here, I can directly get the exact value for the first order derivative at 0.375. So once I know this value, and I already have the values calculated, right? So here for 0.01 step size, 0.1 step size, 0.25 step size, with the second order accuracy, with fourth order accuracy, I have these values. So you can find out the percentage error. Percentage error is approximate value by analytical value by analytical value. Analytical value is this into 100. So this is percent error. Now you can see for second order accuracy, with 0.01 is the fine grid. So the error is very small. And with 0.1, I am getting 6% error. And with 0.25, 36% error I am getting. But if I take fourth order accuracy still very, very small error I am getting. Here previously 0.06, here 0.00052%. So very fine grid and also fourth order accuracy. So we have very, very negligible error. And for 0.1 grid, it is that, and 0.25 grid. So this is with very coarse grid and with low order accuracy. We got 36% error we got. Okay, so this is the way we can calculate. So as I told, there are some few problems in the exercise you have to do in this way. Is it okay? Any questions? So with this, this chapter will be over. And okay, the main thing I want to say. So once I do all these things, so the next classes, what we are going to do is, we are going to go for the finite difference solutions of the actual equations. So if you see the 1D equation, a general equation, we got dou u by dou t plus u dou u by dou x. Because it is first order or 1D, I am not writing the y derivatives, right? We will have v dou u by dou y plus dou w by w dou u by dou z like that. So is equal to minus dou p by dou x plus mu or mu. Okay. Yeah, actually this will be minus 1 by rho dou p by dou x mu dou square u by dou x square. Okay. So this is the equation. The general equation for one, okay, no body forces. Like this. So what we are going to do is, we are going to solve, find out solving with simple equations. Or it can be, if it is 2D, I'm going to get dou u by dou t plus u dou u by dou x plus v dou u by dou y is equal to minus 1 by rho dou p by dou x plus mu dou square u by dou x square plus dou square u by dou x. Like this. So what we are going to do is, first we take this particular one, how to handle diffusion term. Okay, so this is the simple one, and so Laplace's equation. So elliptic solvers we will do, which we take a simple equation, Laplace's equation. So if you know how to solve it, I understand how to handle this problem. And then we are going to do what is called as parabolic equation. In parabolic equation, what you do is, we take the unsteady term and one diffusion term I will take. That is one dimensional, like this. This is parabolic. Okay, and hyperbolic we are going to do like with unsteady term, and one term I will take here. So initially we will take a dou u by dou x is equal to 0, where a is the sonic velocity and this is linear. Then we are going to do dou u by dou t plus u dou u by dou x, which is non-linear. Okay, then we are going to take this particular equation again without dou p by dou x. Okay, so that is called as dou u by dou t plus u dou u by dou x is equal to mu dou square u by dou x square. Okay, this is we are going to discuss. Then we will take the whole thing. So each is a chapter, right? So this is one chapter, elliptic equations, elliptic solvers, and then parabolic solvers, then hyperbolic solvers linear, and hyperbolic solvers non-linear, and so we call this as scalar representation of Navier-Stokes equations. This is the way this chapter name will be. Okay, so that will be there, and this is for incompressible viscous flows. Okay, then we will do compressible viscous flows. So like this, we are going to go from simple to complex. We try to understand how to handle each term and how that physically works and what type of schemes I have to use for each type of equation. So we are going to discuss that way. So this is our future program. Is it clear?
Okay, sir.
So once you start solving these equations, then we can write the codes also. Okay, elliptic solver we discuss in the class. We write a code for elliptic solver. Parabolic solver we do it, and we write a code for that. Like that, we will go from simple to complex things gradually in the class and also in the lab. Okay, quickly we go for the story if there are no more questions. This is, I think, in recent days, it is his story is kept in the school books also. Nick Vujicic. Have you heard about him? Anybody heard about him?
No, sir.
No, sir.
No or else? Okay, he is a man without limbs. He was born without both legs and hands. Okay, just a central body only will be there. And he is such personality. He is a great uh, warrior, and inspiring personality. So you can just see quickly. Those were the emotions going through Nick Vujicic's parents on the day he was born. Okay, the parents were anxious to see their baby that they are going to have. And the 4th of December 1982 was supposed to be the happiest day of the Yugoslavia-born couple, Dusanka and Borislav, Vujicic's life. But the arrival of their son shocked both the parents, as he was born with tetraamelia syndrome. Tetraamelia syndrome is an extremely rare congenital disorder that results in the absence of all 4 limbs. Only a few people in the world have ever been diagnosed with this illness. And he talks about how, when he was first born, his mother refused to hold him or see him when the nurse brought him out. However, once Nick's parents had accepted their son as part of God's plan, they gave him the most normal childhood that anyone could ask for. He was born with 2 small deformed feet. Okay, smooth, that only feet only, no legs. And has nicknamed one of them his chicken drumstick. Originally, the toes on one of his foot were fused together. On one of the foot, the toes are actually fused, and they have cut it and they made operation for that surgery. However, he underwent a surgery which fixed the toes and allowed him to use them for some basic functions. He uses his toe only for most of the functions. He uses one toe of one foot. Okay. You can see his videos, YouTube videos, really inspiring how he is living like that and how happy he is and how inspiring personality. His speeches also you can see really touching. It was not until Nick was using the 2 feet that he did have as normal functioning hands, performing tasks that people with 4 limbs can accomplish. So whatever people with 4 limbs do, he is trying to do just with the toes. He enjoyed playing marbles and fishing with his father. He also enjoyed playing soccer, which he would do with his brother and cousin. Despite this, he struggled a lot with depression, which haunted him until the age of 13. Because he sees other people with normal and he is different, and naturally it depresses. When asked about his childhood and how he got through such a difficult time looking so different, he states that he had some amazing friends who were always there for him no matter what. Nick also has a very strong Christian faith, and his parents would always remind him in his dark moments that no matter what, he was a creation of God. Okay, you understand that you are a creation of God. After surviving the Great Depression in his early childhood years and even suicidal thoughts, Nick grew up to be a strong and lively teenager. He studied the Bible hard and devoted his life to Jesus. Nothing was stopping him now, not even bullying. Towards the end of high school, Nick started giving talks at his Bible study groups. This would be the first start of great things to come. He graduated high school and started university where he studied a Bachelor of Commerce. Through hard work and determination, Nick graduated from Griffith University at the age of 21. What a fantastic achievement. Although he originally had dreams to work in business and finance, that all changed as soon as he realized how inspiring his story could be to others. He decided that it was his journey to travel the world and give motivational speeches. He has started two companies. The first was started in 2005 and is called Life Without Limbs, which is a Christian international not-profit organization. So far, Nick has traveled to 69 countries all over the world, speaking in churches, hospitals, prisons, schools, stadiums, and orphanages. He had said in the past that he always wanted to have employees, and now he does have that with 50 plus staff members working at Life Without Limbs. And Nick Vujicic is a very well-published author. His first book, which is called Life Without Limbs, Inspiration for a Ridiculously Good Life, has been translated into 30 different languages. He has since gone on to publish 8 other books. He also has been awarded the great honor of being one of the New York Times bestsellers. Nick moved to California in 2002 and met his wife, Kane, in 2008. He got married. He had children also. He had always had doubts that he would find love due to his disability and said that it was unlikely that he would find somebody that would want to spend the rest of their life with him. He didn't expect that some girl will come and marry him. The pair both say that when they met, it was love at first sight, and Kane said she knew right away that he was not only boyfriend material but also husband material. Nick even got very creative when proposing to the love of his life. After asking Kane if he could kiss her hands, she felt a biting sensation and then realized that he had used his mouth to put on an engagement ring. How unique and beautiful this story is. It would be normal for the curious mind to question whether or not the pair are capable of having children. But once again, not long after their marriage, Nick proved to the world that there is truly nothing that will stop him from doing what he wants to do in life. Kane and Nick gave birth to their first baby boy in 2013, and you can see how he plays with the children in the YouTube videos. They now have 4 children together and live in Southern California. Currently, Nick has a huge presence in the online and social media worlds. He has 1.2 million Instagram followers and over 400,000 Twitter followers. Nick has a YouTube channel and also has his podcast. From traveling the world to meeting politicians, Nick Vujicic is inspiring millions of people worldwide. He truly is a remarkable man who will stop at nothing to achieve his goals. Being able to make your dreams come true and then use story to help others is such a powerful gift, and you can't help by being touched watching Nick Vujicic use his sense of humor and his sense of humor also when you listen to his speech, it is so humorous, and attitude to do great things around the world. Okay, so he says, you can either be angry for what you don't have or be thankful for what you do have. He says, I honestly didn't think miracles could ever come from my broken pieces, and I was disabled in fear that my dreams would always remain as dreams. But don't give up on you. Don't give up on God, and don't give up on love. Don't give up and know that there is always someone out there who believes in you and who loves you and just the way that you are. I know for certain that God does not make mistakes, but he does make miracles. I am the one, and you are too. Thank you. Thank you very much. See you tomorrow.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you. Thank you very much.
Thank you very much.
Thank you, sir.